All right, so we are, to say the least, a little behind, and I think it's because of the questions, which I also think are good. I am willing to go either way, but I'm not possibly going to get through all the slides if we have the same level of questions. I probably won't anyway, but I'm going to get started. If you feel you have a question that just really you need it in order to understand, please go ahead and ask. If it's a question that you can talk to me about afterwards, let's try to do that. And with that said, the thing I talked about here is really a pretty edgy technique. It does achieve a purpose. I think it's a reasonable thing to do if you're trying to present a view to a client where you really don't want the client to have access to everything that you're doing right now, and you want to distribute it in your own time. What was that? Oh, that was water. Okay, that scared me. All right, anyway, so as I said, this is an edgy thing. It's really not, if you don't feel this is the right thing to do, that's perfectly fine. Some people don't feel they need to provide wrapper components. They just trust their client to do the right thing, and then some don't. Okay, so now we're just going to touch on a couple of more things. We're going to move to the next section. One thing I want to say is that package naming, which we hadn't talked about until now, is more than just a convention. You don't get to name your components any old thing because there are consequences. So if you look at this example, we have sub-C and sub-M packages. The sub-C packages, the sub-C components are client-facing, and the sub-M components are not intended for client use, which is a way of organizing something. But when you look at the physical ramifications, here are the implementation components, here are the interface components. It turns out that you can see clearly that the sub-C package depends on the sub-M package, and similarly back, and that's not okay. So we can't do this, even though we might want to. So at a minimum, we're going to need 3 packages to wrap this up. The wrapper sub-W package and the value semantic types that flow through the wrapper package down at the bottom. And so another possibility is we could break it up into yet more where we have things that flow through the interface and don't and whatever. But the bottom line is this is a group of packages that together serve some function. So we call this a package group, but we're not willing to increase the naming beyond just the few letters sub-W, sub-M, and sub-P and sub-T. Notice the implementation package name is a little longer than the interface package name by design. So this is a package group, and the way we're going to name package groups without taking up any more space is we're going to say that the first 3 letters of each package in the package group are the same, and that is the name of the group. And therefore, groups need to be unique throughout the enterprise because those 3 letters are the way you mint additional packages in your area. So sub is the name of this package group and has exactly three characters. And that's it. That's by fiat. Okay, discussion on that. That was all I had left for the last section. Why not folders? I want to have a name. Oh, are you saying you want to have a hierarchy? The reason for not having a hierarchy is that affects deployment. Right now, I can put any component.o file in any archive, and I can put any header anywhere in the enterprise in any deployment directory, any header file directory. Once you do that, you're tying the directory structure into the machinery of the component, which inhibits me. And I don't like to be inhibited. Okay? Good. Yes?
What about using namespaces?
That isn't going to help you physically.
But they also can be nested.
Well, they can be nested, but we took care of that.
But who cares about function names?
No, we care that the name not be sub : sub m : function name. We don't want to do that. We want to have just sub m and have that work. We want the names to be short. That's really important to us. We'd much rather have the name be short so you don't use using. If you use using, the whole point of this is lost. The namespace is sub-m, the package group name is sub. It all just works. But package names are unique throughout the enterprise by construction. Okay. So, here are some questions, if you'd like to review. This is just section 3.5 of my new book, I hate to say.
New book.
Yeah, it's chapter 5 of the old one.
And the old one has all the techniques?
It has all the techniques.
Including this factoring and escalating?
Yes, including those. It doesn't have as many examples of callbacks. It doesn't have the final escalating encapsulation technique. Yes.
Is the order important? I mean, also preferred to others, or?
The order is in the order that I thought of them. Pretty much. Or the order I felt like writing about them in 1995 or 94. It's a fine order, I think. You know, if escalation works, do it, right? If that doesn't work, demotion, do it. The simple ones are first, and then it gets, you know, redundancies probably should come before a couple of others. Yes?
Summarize, like, would it be fair to say that the most important thing is to remove cyclical dependencies? Like, this is the base of everything.
You remove cyclic, excessive, or otherwise inappropriate dependencies. Physical dependencies, link time dependencies. Yes?
I was going to say that's the axiom that all this is predicated on. That you can't levelize something means
Yes.
to remove the cyclical dependencies.
Levelize, yes, but you can use them to reduce dependencies as well. You can factor things. You can do. This is for removing cyclic dependencies primarily, yes. Okay, but we're done with that now. We're going to talk about some other kind of dependencies. This is the bonus part. This is the follow-on. Okay? All right. So the next thing we're going to talk about is insulation, which is the analogous to encapsulation. This has to do with compile time coupling. So insulation. Logical encapsulation versus physical insulation, an implementation detail of a component, type, data, or function that can be altered, added, or removed without forcing clients to rework their code is said to be encapsulated. Okay? Now I'm going to read another one. An implementation detail of a component, type, data, or function that can be altered, added, or removed without forcing clients to recompile is said to be insulated. So, here we have a collection. Now this time the dependencies are pointing up. It was easier to do that way. Not sure it's the best idea, but anyway, here's your client. This is the caller. And here's a library component. And here is an imp detail. Okay? Now, if I make a change to this imp detail, you notice that it's included by the library component's header, and therefore the library component has to recompile and the client has to recompile. Okay? D is encapsulated by C because when that change happens, the client did not need to rework code. So it's an encapsulated change. Does that make sense? Okay. But really, we mean the use of D is encapsulated. So D, the use of D at all, is not visible to the client programmatically. That's the point. Now, here we have implementation detail E. Suppose it changes. It's included by C's .cpp file. When it changes, the library component has to recompile, but not the client. So E is insulated by C, or the use of E is insulated by C. You see what I mean by use of? There's nothing, E is still available, it's still usable, but that C uses it is not available to the client in any way. Okay? Does it make sense what the difference is? Okay. So, one of the rules that we talked about is a header file, this is property 1, A header file must be self-sufficient with respect to compilation. Okay? So there are 5 reasons to include a header in a header. Reason number 1 is ISA, must do it. Reason number 2 is HASA. Can you think of what reason number 3 might be? What's another reason you might, yeah? Uses? Uses type definitions. What? Uses in the implementation? No. Turns out uses in the interface and implementation is not a reason to include something in a header file. Okay. These are the reasons. If something is or has a, that is a reason to include something in include. Okay. If you have, this is an example, right? These are points that are these are examples of things that are used in the interface. But I don't, just because I use it in the interface doesn't mean I have to include it. I can forward declare it. Okay. So that's the point. Uses in the interface. HASA is uses in the implementation. But you can use something in the implementation without having it be HASA. Like holdsa is a pointer to the thing, and that's different. So if it's embedded data, yes. I can do this. This is fine. Just class point works perfectly. So I don't need to do this. That's not necessary. I can do this. Just pointing out, right? Even though it returns it, I don't need to include, as long as it's not an inline function. So inline, if I have an inline function body, then yes, I do. The 4th one is enum. And the 5th one is type def, e.g. to a template specialization. So that's another example. And yet there's another one, which is covariant return types is another edge case. But basically the 5 is a, has a, inline, enum, and type def. Those are the ones where you might need to include a header and a header. Otherwise, you want to try to avoid that. All right, so next subsection is we have 3 total insulation techniques. These are techniques for fully insulating everything that's going on, not partially, but totally. So first one is the abstract interface or protocol class. And so here's the service and here's the client, and it doesn't matter what goes on in the real service because there's absolutely no coupling whatsoever. So this not only is free of compile time coupling, it's free of link time coupling, it's completely independent. So that's just great. And this is clearly an architecturally significant design. It's not something you can do locally. You have to design your system to do this. Okay, so here's an example where we have a bunch of widgets and we have a framework that uses the widgets. And the nice thing about this is it's very good for decoupling systems. Okay, now if I want to, I can factor out of the widget a partial implementation so that the widget is pure. This is a very important design principle. And if we were talking all about inheritance and whatever, I would talk about this for hours, but we're not. So the idea is you don't want to have any implementation in your protocol. We call that a protocol. Then whatever factoring we intend to do, we'll move that up by 1 level. But the partial implementation is typically not instantiable. And then the final widgets will fill in the blanks. Not override existing functionality, but fill in those that weren't filled in before. Okay. Okay. So, is that clear? Okay. Now, there's this ugly name, this pimple thing. Pointer to impl or pimple. All right. I used to call it a fully insulating concrete class. Basically what it is you have this concrete class and it has an implementation, and the only thing you have in the class is a pointer to that implementation. And so there's really nothing different between every class that's a pimple and every other class that's a pimple. It just has a pointer to its impl, and it looks like this. And so here's my class, and it has some member data, and it has some creators, and there they are. And here I have manipulators and accessors represented by this one thing because I didn't have room. And accessors should be const qualified, but I ran out of room for that too. And so free operators, and they're down here at the bottom. And so this is the implementation. So struct my class impl, and it's just a forward declaration. And here it is over here. And we duplicate all the member data and creators. So we do that right off the bat. And then we replace the data with a single pointer to impl. So instead of having ddata, we point to the my class impl, which is the instance there. And then we need to eliminate all the inline functions because that's compile time coupling, so they go away. And then what do we have? Now we have my int data with the const because there's room now. And what's next? Okay, so now we have to implement this constructor, and what does it do? It allocates the impl, and there's new. And in practice, we would also deal with allocators. But if we did that, then things would become much more ugly. So we will ignore them for now, just for simplicity. And so this is what it's going to look like. This is my class. This is the copy constructor. And so to delete it, we have to delete the impl. And then the data, we're just going to indirect to the data directly. So it's just accessed directly. We don't bother to try to wrap the accessors in the impl because really it's just private data anyway. So this is typically how we do the conversion. It's very mechanical and it just works. The problem is there's an extra indirection when we do it. So clearly if you're going to insulate something, do it early in the project, and then once things have become stable, you might want to uninsulate it. But if you're going to do it, you're going to get the most bang for your buck early when you're making changes. So this is not architecturally significant. Unlike levelization techniques, this is something you can do incrementally back and forth. One thing you want to make absolutely sure is you do not expose the impl in the interface. It is purely an implementation detail of each individual component, class. Questions? Yes? Using an internal buffer. I do not understand.
Say instead of a pointer to my class, you have just 128 chars, and you place new your implementation inside the buffer.
No, I haven't considered that. Why would I want to consider that?
Because then you don't have the indirection.
But then you're exposing the size of your implementation to the client.
The size is yes. That may not be as that may not change.
I think that defeats a large part of the purpose. Every single pointed implementation class looks the same physically as every other one. What you've said is they come in different sizes, 64, 128, 256, whatever. So the answer is no, I haven't thought of it. Now that I've thought of it, I still probably wouldn't do it. But I understand what you're saying. I probably wouldn't do even the pointer to impl one anyway, because it's not typically that important. Sometimes it is. But when it is, that's the most flexible to do. Interesting. Okay. All right. Any other thoughts? Okay. So the next one is the procedural interface. This is here mostly for reference. I just want you to pick up the high-level ideas, but I put some code in here. Actually, I had to put on my reading glasses because I wouldn't be able to read it if I didn't talk about it. Anyway, we have some subsystem, and it works fine in C++. And now we're going to write C-like functions that deal with it. And the C-like functions are a thin wrapper. They don't do anything else but translate from a C-like procedural interface to the C++. And so all of this stuff is the object-oriented subsystem, and this is the procedural interface. And every procedural interface function is independent, entirely independent of every other function. So it's physically separate from any C++ components. We don't mix them in. It's totally devoid of additional implementation beyond that needed for insulation purposes. It's named in a natural, regular, and predictable way. This is hard because we obviously have overloading and lots of strange functions and operators in C++. We have to come up with some sort of equivalent names in C, and they are inherently ugly. They need to be callable from both C and C++ immediately, so we have to do some stuff to make that work. And exposing the actual underlying opaque C++ types is a good thing because then we can mix and match. We can even grant some additional information outside the procedural interface to create and insert from a C++ client stuff that could be done quicker if it were done in C++ rather than through the procedural interface. So that's an example. Here's a point class, and point class, it has this internal include guard and enterprise-wide namespace that we alighted. So here is we have the header and the CPP, and this is, we always have a CPP, of course, and this is always first, as we discussed. And all of our code lives in this global namespace, and only member functions are in the package namespace, meaning if we have member functions, that's fine, but if we have free functions, they're going to live outside the package namespace. So here's an example. We have this thing that's an operator angle, and you can see that it's qualified. And the reason for this is if we didn't do this, if we tried to put it inside the namespace, we could get an overload error. It's one of the reasons why we do our utility classes as static methods of a struct rather than doing namespace. It's just one reason, though. All right. So here is my wrapper, my Z. B uses the same name. It just puts a Z underscore in front, and it's completely arbitrary, but this is the corresponding wrapper for this component. So there it is. Notice the Z. Notice the include guards have the Z. The Z prefix provides the one-to-one mapping. All right, and then you'll notice over here with the creators, we have all of our nice little Z's in front to match what we need. And so I added those. And if we're in C, we're using this part. And if we're in C++, we're using this part. So that's fine. And then, okay, what's next? Move that over, okay. And so this is the correspondence between the procedural interface and the underlying interface. And if you look at it line by line, this is the default constructor, this is the value constructor, this is the copy constructor, this is the destructor. And you can see it's just a mechanical transformation, and it's not pretty, but I'm just illustrating what it might look like. Does it sort of make sense at a high level? You get the idea? It's not particularly exciting. It's here for reference, and this is the CPP file for the interface, for the procedural interface header, and just in clumps, we'll just take examples of what it might look like. And I'm putting it here again for reference. It's going to be on the slides, which are going to be distributed. So I thought for completeness I'd do this. Yes.
If the point and not the point, if it would be a class that has virtual functions, then we would not be able to do that. We would have to use point pointer or.
I'm not sure. You said a class that has virtual functions.
Right. So if the point, not that point, should do that,
Suppose I have a class that has virtual functions. Yes.
how would you be able to pass it to a C function?
I don't. That's the part I don't understand. The class itself has virtual functions, right? So
If the point, let's say a point has a virtual function,
yes.
what would be the interface? C interface?
I think the answer to the question is it doesn't matter because you're passing the address of the underlying object. So it doesn't matter whether it has virtual functions or not. Its address is its address. So you pass it out, you have an opaque pointer. You pass it in, it's fine. Now, I think to be fair, you need to implement the static conversions. In other words, when you want to go from the derived class to the base class, you need to generate the transitive closure of all of the derived and base classes and call the right function to do it mechanically. And you want to write a script to do that. But that's beyond the scope of this. I remember when I actually did this, more than 20 years ago, I had to do that. This actually was something I had to do in like 1985, believe it or not, or like not 1985, like 1990. This is old stuff. This is like ancient stuff. I just want to mention it, but you can do it. You can do from one base class to derived class and back in C. You just have to take the derived class, go inside the function, and come back with the base class. It's just like a static cast. That's all it is. Make sense? Okay. All right. So now this is just a quick plug for defensive programming. We use CAssert because we want to make sure that whenever we have what's called a narrow function, narrow contract, we want to assert that the contract is being followed in a debug or safe mode. And we happen to have this thing called BSLS assert, which is in our public distribution. You can go to GitHub Bloomberg, and you'll find in the BSL package group, you'll see this thing called BSLS assert, and it's part of what we're trying to standardize right now. It's not exactly the same in the standard. It's actually gotten twisted a little bit. That's what happens when you're on a committee, but it's more general than what we have. Of course, what we have works really well, but it's library-based, and the standard is going to go to a language-based approach if it gets accepted. The thing is, all of these asserts would be here in anything that we did in the procedural interface. And so trouble is, if you put this stuff in, you could possibly return through C code with an exception. And we got to be careful we don't do that. Now, it's not necessary for this particular mechanism for you to throw an exception. You can abort, you can do whatever you want. But if you happen to choose to throw an exception on a precondition error and it goes through C code, who knows what's going to happen. So that could be ugly. This is clearly an architecturally significant technique. It's not something that you can just change willy-nilly. You're really moving out of the C++ language into another language. So this is clearly a boundary. Discussion on that. I wrote that myself in PowerPoint. I have nothing better to do. Okay. All right. So now we talked about general techniques, global techniques. Now we're going to talk about partial implementation techniques. I think these are very important because we want to be aware of when we're just giving up coupling for no reason. We're just saying, sure, let's couple the whole thing together. Templates tend to do this as well, sometimes in certain contexts. But when we're just coding, we're not worried about templates. We could still be very lax and couple things that don't need to be coupled. What's worse is sometimes when you couple things, you're stuck. And there's a particular case where a long time ago, I was working at Bear Stearns at the time, and I had written a hash map, and the hash map, I think it was a hash map. Yeah, I think it was a hash map. Anyway, hope I'm telling the truth. Anyway, it was a node-based container, and whenever I needed a node, it would allocate, I think it was 100 elements and sew them onto a free list, and then it would use them one at a time, and whenever it needed more, it'd allocate 100. And this was fine, it seemed to me, until one fine day, somebody decided they would create an array of 1 million of these node-based containers and populate them sparsely with like 1 or 2 nodes. And of course, at that point, the whole thing blew up, and they said, you got to fix this right away. Now, it turns out that I was at the time aware of installation techniques, and so my memory strategy for my pool was not exposed in the header. It was all done in the implementation. So all I needed to do was change that number from 100 to 32, compile it, put the .o in front of the library, which is essentially a patch, and it all worked within a couple of hours. Had I not done that, had it been in the header file and compile time coupled, it would have had to go through the middleware, and those people were on vacation or whatever, and by the time they released that, I would have been fired. So the thing is, I got it right away with a patch because it was an insulated change. And then later we could work through the proper release channels. Okay, so that's really, really important to be able to just drop something in where you can. And so that's why this technique is super important. It saved my bacon and it could save yours. And besides that, it's just way more efficient in terms of rebuilding your software when you don't put everything out for the compiler to have to redo. So the first example is just const access to an array. So here's an example where I've got some data and I want to be able to return the data. Now I could put the data in a static buffer in an array. I could just put it right there and it would be plopped down in every single translation unit. And if you had to change it, well, then everybody'd have to recompile. But I don't have to do that. What I've done here is I've got this in as a data member. I have something that I just ask for the whatever data entry I want by index, and it just returns that information. And I can get the length the same way, just by asking how long is this thing. So I could easily iterate over it by getting the length and saying for I equals this, blah, 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 and get whatever I wanted. Now, the data is in the CPP file, but I don't want to pay for anything. I actually want it to be just as fast as if it were in the header file. And it turns out that here's my data, and everything is done at compile time. It's all set up at compile time. So there's really no runtime operation at all. When I go to access the data, it just works. It's just as good because all that information is right there and available without having to do any indirection. Now, if I change the data, here I'm going to eventually change it. Hold on. Here, I'm going to change the data, and here I go. And when I do this, all I have to do is recompile the util. No other client has to recompile because nothing in the header file changed. It's all the same stuff. Do you see how that works? So it's a little bit of extra work, but why not? Because if you want to change the data, if that's important to have flexibility, there you go. This is how you do it. Okay? Make sense? Possibly? All right. That was not too hard. Discussion? Yeah.
Can it be by chance that some smart guy caches the size that is static constant?
Smart guy does what? Static constant of what?
Cache the size. Okay, it's 7.
When I say change it, I'm talking about on the order of days, not while it's running. Right? I'm changing the source code, recompiling my stuff, relinking the program, statically linking the program. So it's not the running program. Does that make sense? It's not, there's nothing to cache, unless you're saying he caches it in a database.
No, I'm just thinking if there is a too smart compiler.
Okay, there's no compiler that's smart or dumb, depending on how you want to work it. Okay. All right, next is what I'm going to call a toy stack. So I've got this stack. It's really dumb. It's just a stack of integers. I hope I'm telling the truth. Is it a stack of integers? Yes. No, it's a stack of toys. That's what it is. It's a toy stack, of course. It would have to be a stack of toys. All right. Anyway, so this is the interface, and it's just to illustrate what's going on. We know how a stack works. We construct one, and this is what the constructor for a stack looks like, let's say. And then we want to push a toy onto the stack. And so this is what that looks like. So this is all in the implementation, right? It's all completely insulated. There's nothing going on that you can see except for the 3 data members, right? Now, suppose we want to push this to inline to make it faster. So we do that. So now push has this inline. Please keep in mind that I would never really put this code right under the function. It would be down below. It would say inline, and it would be separate from it. But because this is a presentation, I took some liberties. So now this is what's going on. If d_length equals capacity, then we're going to resize. Otherwise, hold on. Yeah, we're going to resize. Yes. Then we're going to unconditionally do this new thing and whatever. By the way, I always put braces around ifs unless I didn't have room on the slide. So this was hard for me to read. Anyway, so this is If this is not true, then I'm going to just jump over that and do what I need to do. And notice that I'm doing a lot of memory management stuff in line, and that's not usually a good idea. Did I say that? No, that's not true. I forget that I said there's a lot of stuff going on here. What I meant to say was I'm not doing the memory management stuff in line because the resize is going to do the memory management out of line. What I'm doing here is just what I need to do to grow the stack. So the next thing here is suppose they are equal, yes. Well, then I'm going to call this resize function, which means I'm going to jump to the private function, which is my entry into the CPP file. That's what I'm doing. I'm going from the inline function to a private function that's not inline, and that not private inline function resize is going to do the work that I needed to do. And it says if the capacity is 0, make it 1, otherwise double it. So that's my strategy that I'm going to use for growing my stack size. And this can be an insulated change. What if I want to change it to 2 or 1.5 times? I can do that, and my client doesn't have to recompile, even though the stack push method was inline, because the hard work was factored out and put in the CPP file. Okay? This is called a partial insulation technique. Had I put all of the code into the interface, number one, it would bloat the code. Number two, I couldn't change it if I wanted to without recompiling all my clients. And number three, the includes that my clients would presumably have to deal with, like whatever other things, any other includes, for example, if I had to include anything having to do with allocation or memory or whatever other kinds of things. This is also typical of like I/O streams, where you don't need to put all of the code in the header file because you can sequester it in the CPP file. That's the third reason. So you cut down on the dependencies, you cut down on the code bloat, and you increase the ability to change it without forcing clients to recompile. All positive benefits. And maybe I want to do this insulated optimization where I change a copy to a move. Again, it's all in the CPP file. I don't have to worry that my client is going to have to recompile. It's all sequestered there. Okay? So, discussion on my toy stack. Make sense? The idea is the same. We're moving stuff that we can that doesn't happen very often, is very expensive, has lots of dependencies. We're moving that to the CPP file. So when we change it, our client doesn't have to recompile. All right, the next one, an adaptive memory pool, simplified. So here I have this basis for actually a multi-pool allocator. And the idea is it has allocate and deallocate, and it allocates pools of different sizes. And this is just what I just said. Okay, so for example, this has three allocations worth, and you'll notice that each time I allocate a new thing, it doubles in size. So first time I allocate 1, then when it runs out, I allocate 2 more and use 1. When the second one is called, I run out, I allocate 4, and so on. And here, this is much bigger size objects, right? So I have all these different objects running up from here to here. Now, if there's nothing needed of that size, there's nothing there. It's empty. So this is like, I call it a beanstalk. There's all these different size pools, these adaptive pools, which when requested, give you initially 1, then 2, then 4, then 8, and so on. Okay, so if something comes in that's too big, we just put it on the sort of the too big list. These are oversized things. So that's how that generally works. The one that we've been using a lot is pools of size 56. So once I get to 32, I didn't bother to go larger, but with the design we have right now, it wouldn't hurt if I just kept going forever. It doesn't matter. So how does this work? Let's take a look at just one pool. So the pool, it has a list of blocks, and then it has, okay, then that's and then, well, this is the memory blocks of arbitrary size. Okay, and then it has the block size, which is 56 bytes here. That's the one that we're interested in. We have the chunk size, which is how many of these blocks of size 56 do we have? And then and that's showing that. We have the begin pointer, and that's saying where the next memory is going to come from. And we have the one past the end pointer, which says where I'm going to be when I get to the end. We have the free list, and the free list is the list of things that have been put back because somebody did a deallocation. So this is a state of this adaptive memory pool. And okay, so now I'm not going to talk about what's inside the pool. I'm just going to sort of talk about the interface for now. And so these are all empty lists. This is what's being maintained. And so this was created with a size of 56. And this is an arbitrary sentinel. And it turns out if you look closely, there might be a better sentinel value. We'll see. And that's 1. And y is not all that important. But anyway, so let's say I want to allocate. So if I allocate, what happens? It allocates one thing and it's returned. And then, so that's now if I allocate again, it allocates 2 and returns the first one of those. And then if I call deallocate, then it returns the one I just had and puts it on the free list. And then if I call allocate, it returns the second one, deliberately returns the next one here because it's faster. Okay, and then if I call allocate again, then it decides to look at the free list before it allocates again, and it returns that one. And this continues, you allocate something, and now it needs to allocate 4 and return 1, and in time, this is what happens. So anyway, this is the implementation, and yeah, this is just straightforward. I'm just sort of highlighting what it looks like. Okay, and here's the deallocate. Now, this is what we need to do to link something onto the free list, and if there's something available. So here's really the point. This is what we have to do to allocate something. If there's a block available in the current chunk, then we're going to do this. This is the fully insulated implementation. And then if there's not, we're going to check the free list. And if not that, then we're just going to create a new block. So these are 3 different parts of what needs to happen when we do an allocate. So now, hold on a second. So now we're going to put all of this stuff here in the header file, and we're going to say if, so we're going to move some of the implementation to the CPP file, but we're going to keep the most important stuff. So in this case, if I change the max chunk size from say 32 to 64, I can do this. I can add a special case, and we get a speed improvement, and I can change that, and we get a space improvement. But these are all changes that I can make in the implementation without affecting the client. And so what's happening here is again a partial insulation, and it allows me to facilitate performance tuning. Think about it this way. If you had to recompile the world every time you tweaked your implementation, you wouldn't tweak it that much. But if you can tweak it, link it in and run it, tweak it, link it in and run it, tweak it, link it in and run it, then it's going to make things go a lot easier for you. So it really is a kind of important thing. There's another way we could break this out too. We could make things smaller. Partial insulation reduces code bloat. If there's so for example, if there's a block in the current chunk, return it as quickly as possible. So now what we've done is we said, there's a part of this that I really want to run fast. So I don't have to do all or nothing. I can say, you know what, I'm gonna take a little bit of this out and put it in the header file, and that's okay. Otherwise, I'm gonna do the rest of it. So it says that, and then anyway, the idea is you can do as much or as little in the header file as you think is appropriate. The more you do in the header file, the more there's code bloat, but at the same time, maybe it's the part that gets exercised the most. So it might make a lot of sense to do the first attempt at acquiring something right away. And then if that doesn't work, then you say, well, it's very infrequent. I have to go to the free list or reallocate a new block. So I'll do that in the CPP file. But as far as just trying to see if I have room to quickly return one link, let me put that in the header file. Let me put that in the inline function. So that's what that's talking about. Okay. So discussion on that. That's a lot of code late in the day. I didn't want to go through it. It's on record. You'll be able to see it on this at your own leisure and read it. But at this point, going over it line by line is probably not worthwhile. Do you get the idea, though, that there's some parts that are used a lot, not very big, don't have a lot of dependencies, don't need to be tweaked because that strategy is stable? Put that in the header file. Put the rest of the stuff that needs to be tweaked in the CPP file using a carryover by calling a private method that goes over into the CPP file. Yes? Link time code generation. I don't know what that is.
The code is not just the whole program optimization.
I don't know what you mean by can't. You certainly can do it. This is designed to be used in a conventional.
End up building a lot more, linking a lot more.
Well, as I said, the idea here is if you put stuff in the CPP file, then when you change something and recompile your stuff, the other people don't need to recompile their code because your header file didn't change. Now, if you're doing whole program optimization, it's not a very large program, so it doesn't really matter. Oh dear. Well, that's not my understanding. I don't know what very large is to you, but if we tried to use whole program optimization, whatever it was that was doing that would catch fire and burn. So I don't know. But I don't even know how to answer that. But I'm telling you that the purpose of this is for conventional builds, static libraries. This is how we would make it easier for people to fine-tune their performance without having to rebuild the world. That's my answer, I think. Any questions on this? No? Yes? Good? All right. So here are some questions that you could ask yourself about what I just talked about. So how about this one? Why, when would you put a pound include directive in a header file? Do you remember? Inline? Yeah. Type def to template. Yes. Good. That was excellent. Okay. So there are 5 reasons. And of course, covariant return types. Okay. Which total installation technique is not architectural? Yeah. Oh, good. Pimple. Dang. It's great. All right. I really don't have time to do this last one, but I can start and we'll just see how close I get. Okay. So the whole thing that we've been talking about, the way we do architecture, is based on organizing principles, and the most important one of those is sound physical design. So this is an example of how we create a big ball of mud. We start out as developers and we say, I've got an application and I have a library, and that's good because you want to separate your library code from your application code. So if somebody else comes along, they can use your library code without mucking with your application. And somebody else comes along and said, well, I know you guys don't need this stuff, but somebody else might, so I'm going to build it this way. And it's good. And then somebody comes along and doesn't play fair and decides to have an application depend on another application. The applications are malleable and therefore they change, and therefore App 4 becomes very unhappy because the code stops working, right? Whereas the libraries are stable, the apps are not. So this is bad. And of course we have, continue to work, and then somebody gets this crazy idea of pointing a physical dependency up. We don't ever point physical dependencies up with the one exception of the installation slides because that was easier. But we don't do that. But anyway, it's still not a cycle. Now it's a cycle. Now we have libc and the second version of lib-a, cyclically dependent, mutually dependent. That's not good. And then library D comes along. It's still kind of okay. And now it's all gone to hell in a handbasket because we have a large cycle in our design. And then, App 4 is doing its thing, and then everybody stops caring. and then it starts to look like this, and then pretty soon it starts to look like this, and this is not good. And then it starts to look like this, and this is really not good, and oh well. So good physical design is it's an engineering discipline, not an afterthought. We have to do it from its inception, and at the very point where you try to decompose the problem into separate problems that you're going to try to solve separately and then recombine into a final solution. If you separate them this way, you're doomed. If you separate them this way or this way and then solve them bottom up, you might do okay. So that's the sort of the very high level advice, if you will. Okay, so here's an example of a design that it'd be reasonable. You can imagine creating something like a logger, and the logger depends on a lot of software, reusable software, and that's good. And then, you have this transport, and the transport depends on the logger, which that's because transports have lots of problems, and when they have problems, you want to log whatever's going on there. Now we're sort of at an application level. And then, of course, you might want to build a mail system on top of some sort of transport. So that's a good thing. And it has its own little bit of implementation components. We like that. And then what happens? Somebody comes along and says, that transport is so flaky, the next time something bad happens, I want the logger to send me a mail message, and that's this. And that's a bad idea. So we do not want that to happen. Now, one of the examples we used, I think we saw this, is that we can use indirection. We can use a protocol to fix this. And the typical example is we have an observer in the logger where we can register an adapter. And then we can test the logger, the transport, the mail system, and then finally we can test the adapter by registering it in the logger, knowing that the logger, transport, and mail system work. So this is a good thing. So when we're designing, think like this and not like this, of course. The next one is, don't build a date class that looks like this, right? We don't want to do that. This is the date that depends on everything. Anyway, it was once said when I was at Bear Stearns, it was suggested, they're out of business now, so I can say this. We hired a consulting company, and they were obviously a little confused. They suggested the standard layered approach, where we have the data access layer and the business object layer and the control object layer and the presentation layer. And oh, by the way, we're going to write it in Java. It's going to be awesome. And the problem is that they wrote classes like this, where clearly the data, the leaf level data types depended directly on the database. And that's like this, right? And of course, that means everything depends on the database. And you can't take the database on the train with you when you're trying to work on your code on your laptop. So this was just disastrous. And when my boss at the time, he couldn't believe that they were actually suggesting this. He became irate, went to the head guy, and the head guy called a meeting, and they pointed at me and said, John, tell him what you think. And so I started, and then he just kind of said, okay. And then he said, so what's up? You sent your B team? Oh, that was awesome. Anyway, I thought I was going to get fired because they refused to work on the project unless I had nothing to do with it. And it was actually very good because the deal didn't go through, and it was one of the best things that could have happened. They were charging like more than $50 million for nothing. So turned out I did a good thing. But anyway, water under the bridge. But it is a true story. Anyway, so here we have an example of what I would call a lateral architecture, where the business objects or the value types are at the bottom. They're very lightweight. They represent values, but they're not glued into anything else. The business logic uses the value types. The business loaders read the database and populate the business types. And then there's something at the top that coordinates the whole thing. So this is a lateral architecture, not a layered architecture. And this could be done in C. It doesn't have to use virtual functions or anything. Now, if you want to get a little more clever, you could do something like this. And here what we have is we have some abstract interfaces that allow us to swap out a database with maybe a different database or maybe just a test database. But in any event, the database is in no way coupled to the rest of the system. So this is a very nice decoupling mechanism, and accessing a database is a perfect example where a virtual function call is not going to hurt you. Even if it goes ahead and calls an indirect pointer, not to worry about it. Okay? I hope everybody trusts me on that one. So anyway, this is a very flexible version of what I just showed you before. Now, if I had time, so what I might do is I might go through this at like 100,000 speed, and I won't explain to you what's going on, but you'll just see. Suppose somebody said, write me a date class that tells me whether today is a business day. Now, the first thing you do is you have to parse that and say, well, that means that I'm going to have something like this, which is kind of like the date class we had before. It's poor logical factoring. It's not flexible. It's just bad. So what do we really want to do? If we were going to solve this problem we don't have time for, we'd say, what are the real requirements? Well, represent a date value as a C++ type, determine what date value today is, determine if a date value is a business day, and provide well-factored useful components that we'll need to over and over again. That would be the goal. We have 1 minute, so I have no idea what to do, but I can just run through these slides, and it would look something like this. Now, we use color, actually, to represent different kinds of types. So mechanisms are green. Those are instantiable types that don't attempt to represent a value. And a day of week is an enumeration. It's blue because it does try. So it's true blue. You know, green is a little closer on the color scheme to things that are not instantiable. And here's a date, which is a value semantic type, so it's a value type. Okay. And this is how we would represent this organization. And then determine what date value today is. Well, it turns out we would need to create a bunch of stuff here. And just to quickly go over it, we'd need this. And the pink thing, by the way, is a util, and then that's its color. So as we go in that direction, they're not instantiable types, and it would look something like this. But you notice we had to do a lot of stuff to get there. And then the next thing is determine if a date value is a business day. All right, well, we got a lot of stuff to do here. So without wasting any time, protocols are yellow. They're between green and pink. And here we go. So we have this, and there's a problem. We don't have a data source because in order to answer this question, we need data. And so we need a calendar cache, right, to go get the calendar, whatever calendar we're using. And of course, we're going to need a calendar loader to go out of this library. And so here's our calendar cache. Now, that's actually in the application area, but it's a mechanism that implements the calendar loader that gets us the data that allows us to access the calendar to do whatever we need to do. And now we're good. And it turns out there are a couple of extra utilities we might want to have. Like we want something, we don't want to put it in date, but we want to get the fourth Wednesday, let's say, or fourth Thursday in November 2016. It's a useful thing to know. We're not going to put it there. We're going to put it in a date util that depends on date and some other things. We might want to do something like modified following for a financial services industry, which means find the next business day at or after the given date. Otherwise, the largest business, the most recent business day in the date before the current date, and we put that there. And now we have the complete picture, and I'm just going to go through this. This is now components, not classes, and I'm just going to really run through this. Now what we're doing is we're backfilling the problem. We're saying, what other things do we need to do to fill in the implementation, even though it's not client-facing? And this is just a little discussion about transitive dependencies, which I'll skip. And so here's an example, client-facing. We'll add some other pieces that we need, and we have, it looks something like this. We're adding all that stuff in on the back end. No one sees it, it's just for us. So it would look something like this. But the truth is it doesn't really look like this. It looks a little more like this. Well, that's not even really true. It looks like this. This is what you need to do what I just said properly. But we already had most of it before we started. So this is our stack. If you have any questions, that's the outline. And here's the conclusion, because I really want to be done with this. And that's the end.